Okay, so we're looking at question number 1 in section 5.1. So let me share my screen. So here we are. You should be seeing my browser window and section 5.1. Let's zoom in a little bit. Okay. This one, the central limit theorem for proportions. When you take samples from a population and compute the proportion from each one, you can consider the distribution of those proportions. This is called the sampling distribution. So this question is about what the central limit theorem tells us. All right, so it says that the sampling distribution is, now you have to choose if it's what kind of distribution it is. All right, I'm not going to answer this right now because it's, I want you to think about it on your own, and I'll go through this in a little bit. So,
no, I know that. The part that gives me trouble is the second question and the third.
Okay. But I still want to go through this. And then with the, okay, well, then you're going to determine what these things are here, whether it's, whether we're talking about its proportion, standard deviation, or mean, all right? And then the mean of the sampling distribution, this part. Well, if you look at the central limit theorem, and we'll take a look at this in a little bit, it actually specifies what the mean is. Now, what they want here is actually a variable, all right? Because I didn't give you any numbers in this problem. So you're expected to write down a variable that represents the mean. And if you just look at this, the central limit theorem, you'll see what variable it is. And then down here, they want an expression involving the variables that occur in the central limit theorem. So the variables, you'll look at the central limit theorem and you'll see that the standard deviation is just given as an expression. And you can enter that expression by using this little up arrow here. You can do some more complicated things involving expressions using these functions here. Okay, so if you want to
but I put the expression, but it said it was wrong.
Well, I've tested this. I was able to put the expression in and it looked like it was working correctly. So I think it should be working. Let's go through. I want to review the central limit theorem anyway. I know we've already talked about it for 2 days now. In the last 2 lectures, we talked about the central limit theorem. But I think it's not the easiest thing to get to grips with. So I think it's worth. I think it might be worth discussing a little bit more anyway. So when we go through that, maybe it'll clarify some things, okay?
I'm sorry, for the second part you said what you had to put?
A variable. There'll be a variable in there.
Okay.
Yeah, the second to last and the last question there involve variables. Okay, so, but before I do this, before I go to the central limit theorem, I just wanted to mention some things. So the first of which is that the next exam is going to be on May 5th. Okay, that's 2 weeks from now. I think that's, let me just check my calendar here. That's exactly 2 weeks. So it's the Tuesday after next Tuesday. Okay, so that will cover everything we talked about in chapters 4 and 5. That's everything since the last exam. On that exam, I'm going to have a couple questions that require you to show your work, like on the last exam. And so those will be weighted a little bit more, the parts where you have to show your work. So be ready for that. I will let you know what kinds of questions I'll ask you to show your work on ahead of the exam so that you can have an idea what you should be prepared for there. Otherwise, the exam will closely resemble the homework. Right? So the best way to study the exam is to study the homework questions. And I will post copies of the homework assignments so that you have access to them and you can go look through them to help you study for the exam.
When would you post it?
I'll put them on my Open Math and I'll post an email.
When?
Oh, I don't know. Probably next week.
Okay.
Also, if there's any, if you have some old homework assignments that you didn't get around to, or if you need more late passes to let you access a recently missed homework assignment, let me know, and I can look into, just email me, and I can look into opening up an old homework assignment or crediting you some more late passes. Okay, so just send me an email if that's what you need. The other thing I wanted to mention is that I graded Lab 3. And so you should look through Lab 3. You should be able to look through there and see the comments that I left. If you did the problem perfectly right, you might not see a comment. But if there were issues with how you answered one of the questions, these are what I'm talking about, are the 2 questions where you had to submit a written response. You should look through those, and if you had some difficulty there, I left a comment. And there was a fair number of comments I had to leave. So for that reason, I want to discuss Lab 3 at the beginning of Thursday's class this week. So please look through Lab 3, read my comments that I left, go back, you can download Lab 3 out of the course materials, and please review that before class on Thursday so that what we talk about makes sense, because it's been a while since we did Lab 3. So if I just start talking about it and you haven't reviewed it, it'll probably be a mystery. So please look through that ahead of class on Thursday, and I'll talk about that. And please look through the comments that I left on that. Okay, any questions before I review the central limit theorem?
What about Lab 2?
All right, say that again.
Did you grade Lab 2?
No, I can't make out what you're saying. I'm sorry. If you could leave a written chat message, I might be able to understand. Your audio is not coming through clearly. That looks like Audra's mic. I'm going to mute your mic, Audra, because I'm hearing a lot of background noise. Oh, I'm seeing some chats coming in. Okay, great. Question 5 in 5.1. Let me take a quick peek at that one. Yeah, we will go through that. I will go through this question. I actually had an idea to go through this right after I talk about the central limit theorem. Did I grade Lab 2? Oh, I think I graded Lab 2 a long time ago. Let me just check. I thought that Lab 3 was the only one that, if I forgot to grade Lab, I think I graded it. Maybe I didn't submit the grades. Let's see. Ooh, the grades weren't submitted for Lab 2. I will check on that. I hope it's not in my office. If it's in my office, we may have to just, well, I'll see. Well, I'll look into Lab 2. I didn't know the grades weren't posted for that one. I'm glad you asked that, though. That's a good question. Okay, so what we're going to do is we're going to look at the central limit theorem. Okay, so let me, I prepared, no, my screen froze. Okay, it's back. I got like a little demo here for that, so let me get that ready. Okay, and then I'll share that screen. All right, so you should be seeing the screen with central limit theorem. Ooh, central limit theorem for proportions. Okay, now I checked out some of the videos that were posted on My Open Math about the central limit theorem, and they're very good. There's some videos in that section. However, they talk about the central limit theorem for means, which is essentially the same, but it is a little bit different. The central limit theorem that we're talking about is the central limit theorem for proportions. They're almost the same, but just keep that in mind. When you look at those videos, they're talking about the one for means, right? So here's where we're going to talk about the central limit theorem for proportions. We already talked about this the last 2 classes. I introduced this 2 classes ago, but I think it's worth reviewing a little bit more. Okay, so here's a little demo I made here. So in this very simple example, I have a grid, right? And what we want to do here is we want to determine the proportion of cells in this grid that contain X's. Well, that problem is very simple. I mean, to compute the proportion, all we have to do is count the number of x's and divide by the total number of cells here, and we got it. But I want to go through this using the methods that we talked about so that we can generalize this to more complicated scenarios, okay? So, like I said, with a population this small and accessible, just the grid we have here, we could determine the proportion just by counting up the x's and dividing by the population size, the number of cells here. There's actually, it's a 5×8 grid, so there's 40 cells. So you could just divide the number of x's by 40 and you'd have the answer. But suppose that we didn't have such a conveniently small and accessible population, as would probably be the case in real life. In real life, you're probably sampling people from the population of humans, and there's many more than just 40 humans out there. There's millions, billions. So it wouldn't be this simple, okay? So we still want to go through the methodology. The best we could do is to make measurements from samples from the population. You would sample people. How can we use statistical methods to estimate the true population proportion from our sample measurements? That's what we were talking about. That's what we want to talk about here. Well, here's the strategy. We're going to take a bunch of simple random samples. Those are samples that are just completely randomly determined from the population and record the proportion of x's in each sample. So that's what you do in real life. You take a sample and look at the proportion in that sample. So that's what we'll do here, okay? So what I did, I actually used StatCrunch to choose. You can actually, there's a feature in StatCrunch where you can actually have it take a random sample. So I just numbered each cell in this grid, numbered 1 through 40. And then I told StatCrunch, choose a simple random sample of those cells. And it spat out a list of 5 cell numbers, and then I highlighted them here, okay? And so now let's take a look at these highlighted cells here. Here's our first simple random sample. It contains 3 x's. Therefore, the sample proportion is 3 out of 5. There's 5 cells, 3 of them are x's, so the sample proportion is 3 out of 5, that's 0.6. Okay, so I just computed that, and let's mark it down. So there it is, 0.6 falls right there. Now let's take another sample. So I had StatCrunch do another simple random sample, and here's what it came up with. And in this sample, it contains 1x. Therefore, the sample proportion is 1 out of 5. That's 0.2. So let's mark that down right over there. All right, and then I did a third sample. Third sample contains 3 x's. So the sample proportion is 3 out of 5. That's 0.6 again. So mark that down right over there. And then I told StatCrunch, you know what, do this a whole bunch of times. I want to have a total of 30 samples. So I had to generate 30 random samples. And here's the next one. That also sample proportion 0.6. Another one, 0.6. Another one, this one came out with 0. 0 x's in that one. Another one, 0.4. Another one, 0.4. And I just kept making random samples and marking down the proportions. And I just kept doing this. And I did it again and again and again until I had 30 samples. So keep going. And what we're doing here is we're generating a distribution of sample proportions. There it is. So now we have 30 sample proportions. And we can look at this distribution. This distribution is called the sampling distribution. All right? The sampling distribution, because it's a distribution, has a mean and it has a standard deviation. The mean is given by P. P is the actual population proportion. That's the true proportion of x's in the population. We got many different proportions from our samples, but the true proportion is P, and that's the mean of this distribution. The standard deviation is denoted sigma, as always, and it's given by this formula. So this is the mean and standard deviation of our distribution. Now, the central limit theorem says there's something very special about this distribution, something very wonderful. The central limit theorem says, oh, I forgot to point out, in this formula for the standard deviation, the n is the size of our sample. In this case, the sample size, in this demo that I did here, the sample size was 5. So each sample took 5 cells. The central limit theorem says the sampling distribution is approximately normal. That's fantastic, because that means that we can just use the normal distribution for this, all right? But it's only normal if these conditions are satisfied. If n times p and n times 1 minus p are both greater than or equal to 10. So we need to check that. That's called the success failure condition. But if we verify that, this central limit theorem is telling us that we can just use the normal distribution. Now, if you look at the distribution pictured here, you can see it's not quite normal. In fact, it's skewed. Why is that? Well, if you were to actually check these conditions, you'll see that they aren't greater than or equal to 10. Doesn't quite work. And that's why this is not quite normal. But if we had a sample size that was large enough, and if instead of taking only 5 members in each sample, if I took 20 or something, we could satisfy the success failure condition, and this would look normal and become symmetric. And that's the wonderful thing that the central limit theorem tells us. It says it's normal. And by the way, in that exercise that was asked about at the beginning of class, this is the information that you need to answer that exercise, right? It asks what is the mean and what is the standard deviation, or maybe it asks what the standard error is. That's the standard deviation of the sampling distribution. Well, here they are, right? So this is what you'll need to answer that question that was asked. Okay, the very first question we looked at. So this is the central limit theorem. It tells us how all this stuff is going to be distributed. Okay. All right. Now let's go to, let's see. We had another question about number 5 in section 5.1. Okay. So let's go to that. Let's use the central limit theorem to see what we can say about that question. Here we go, go into my browser. I'm going to go down to go down to section 5.1 here. We're going to look at, things run slow when I'm running the Zoom. Okay, number 5. All right, it says, suppose 14% of students are veterans. From a sample of 297 students, how unusual would it be to have less than 29 veterans? Okay, let's see if the success failure condition of the central limit theorem is satisfied. Okay, well, we need to check. Remember, the success failure condition had us checking n times p and n times 1 minus p. So what is n and what is p in this situation? Well, p is the population proportion. Well, look at this. This first sentence here says 14% of students are veterans. From that, we can get a proportion. 14% is the same as the proportion 0.14. All right, so our population proportion P is 0.14. What about N? What is N? Well, that's the next statement here. From a sample of 297 students. N is the sample size, so N is 297. So to compute N times P, we're just going to multiply 0.14 times 297. Okay, so let me go over to a calculator here. Come on, calculator. There we go. 0.14 times 297. There it is, 41.58. Is that greater than or equal to 10? You betcha. That's greater than or equal to 10, so good. The other one, maybe I should have done it in reverse, n times p. So n times p, n was this, and p was 0.14, same thing, right? 41.58, that was n times p. The other thing we need to check is n times 1 minus p. So n is 297. 1 minus p, 1 minus 0.14 is 0.86. All right, so there we go. Is that greater than or equal to 10? Yes, it is. So they are both greater than or equal to 10. So I check this. Yes, they are both greater than or equal to 10. So the central limit theorem is satisfied. Fantastic. That means that the distribution, we know it's approximately normal, right? So that's the answer right down here. We know the distribution follows a normal distribution, approximately. And we know the mean and the standard deviation of that distribution. The central limit theorem told us that the mean was p. Remember what was on that slide that I showed you just a moments ago. And what was p? P is 0.14. And what's the standard deviation? Well, the standard deviation was that little more complicated thing. It was the square root business, right? So let's go compute that. It was the square root of p. Oh, p was 0.14 times 1 minus p, 0.86, divided by n, which was 297. 297. Taking the square root of that. There's my standard deviation. I'm going to round it to 4 decimal places. You should always go to 4 decimal places at least on these problems. 0.0201, all right? 0.0201. That's what the central limit theorem tells me. Okay. Given this knowledge, use technology, that means StatCrunch, to compute the probability that through random selection, one finds a sample proportion that is less than or equal to the proportion corresponding to the 29 veterans. Because we're trying to see how unusual is it to have less than 29 veterans. So what's the proportion corresponding to 29 veterans? Well, it's 29 out of 297. All right, so the proportion corresponding to this, the P, let me pull up a, let's go to the calculator. I think that's maybe the best way to do it. 29 divided by 297. This is the sample proportion, what we had called P hat. Right? 0.0976. Okay. I want to know what is the probability of getting a proportion less than this. Okay. Well, what we're going to do is we're going to go over to StatCrunch. So let's go to StatCrunch. Let's open it up. Let me just zoom in. Oh, I think it's zoomed in pretty well. And we're going to go to the central limit theorem told us that the distribution was normal. So we can use the normal distribution here. Okay. We knew what the mean was. We answered that in the first part of the problem. It was 0.14. The standard deviation we wrote down. That was 0.0201. 0.0201. Now we want to know what is the probability that the proportion is less than the proportion that we just calculated. 0.0976. All right, so let me paste that in there. Less, oh, I can't see the zoom controls are in my way. Okay, less than is the same as less than or equal to when you're dealing with a continuous distribution. All right, so you just put this. And here we go. Here's the sampling distribution. This is a picture of that sampling distribution. Here's the proportion that we measured was 0.0976. That's right here. on the left, just shy of 0.1. And the probability of getting a proportion less than that is the area of this shaded region, which StatCrunch tells us is 0.0175, if I round correctly, 0.0175. So that is, if I round correctly, what goes here. That's the probability. Is this result unusual? Okay, well, so unusual, we talked about this last time, unusual means that there's a less than 5% chance of it happening. All right, well, we just computed the probability of it happening, and it was about a 1.75% chance. That's certainly less than 5. So yeah, that is less than 5%. So that is how you would resolve this kind of problem. And I've got 3 or 4 of these problems of this kind in here. Right? Some of them have you measure a proportion, the probability of getting a proportion bigger than what's given. Some of them have you do what's less than what's given. So if you look at this problem here, it's almost exactly the same. How unusual would it be to have more than a certain number of people order French fries in this case? So sometimes you'll have to do a proportion. You're looking at the probability of being greater than. In the last problem, we did less than. What's the next one here? Here's another more than problem. And then a less than problem. So that's how you do these problems here. You could even ask, I could even ask, what's the probability of having a proportion between 2 values? Right? I don't know if I asked any like that in the homework, but that totally would have been a possibility. Okay.
So with question 10.
Question 10. Oh yeah, that is a between question. Yep. So you could totally do that because in StatCrunch, you can hit the between button up here, and you can do between 2 values, right? In this case, it might be interesting to do 0.12 and 0.16. I'm not saying this has anything to do with the problem we were looking at, but when you do you can do the probability between 2 values like this. Okay. So I hope that clarified things. Oh, oops. Hope that clarified things for you. Could you please repeat how you got the standard deviation? Yeah, let me get a video on my sheet of paper here. I just have to log in with my phone so that I can project. I ordered a nice camera to do this, but it looks like not going to arrive till the end of the semester, so that's kind of a bummer. So we'll rely on my phone here. Okay. How did I get the sample? How did I get the standard deviation? So here I'm going to highlight my paper. Okay. So the standard deviation, remember from the central limit theorem says the standard deviation is square root of p times 1 minus p over n. All right. And we said that p was 0.14 and n was 297 in that problem we worked out. And so all I did is just plug that in here. Right? So p, 0.14. 1 minus p is just 1 minus this, right? 1 minus 0.14 is 0.86. So, and then I divided by n, which was 297. And that's what we computed on the calculator. Right? And we got 0.0201 approximately. I rounded. Right? So that's how we get the standard deviation. Okay, another question. How did you get the proportion for the second part of 5? Okay, yeah. So in the second part of the problem, we needed to find, we asked, what is the probability of getting a proportion less than the one corresponding to the number of veterans that was observed, or something like that. So that is p hat. All right, p hat is you observe it, you go out and just measure a certain proportion, right, and just see what you get. All right, these are like the proportions that we used when we built up that distribution in that first example I gave, and that when I was building up that distribution. Let me. I don't remember what the problem said. Let me just take a peek here. Oh, we had 29 veterans we observed. All right, we were asking. It was a question about what's the probability of getting less than 29 veterans. Well, then we have 29 over 297. Right, and oh, yeah. What did we get there? Let's see, that was 29 divided by 297. We got 0.0976. And so what we were looking for in that problem is we were looking for the probability of measuring a proportion, a sample proportion, a different sample proportion, less than this. 0.0976. So this is one sample proportion, but if you go out and take another sample, you'd get a different sample proportion. You get all kinds of sample proportions. They vary from sample to sample. What's the probability that the sample proportion that you end up getting is less than that? And that's what we computed using StatCrunch. In StatCrunch, we set up that distribution, and we computed this, and oh, I forgot what we got. I deleted it off the screen now, but you should remember what we had there. Or you can look back at the video and see. Okay, any other questions? .0175, okay, thank you. 0.0175. Right here. Okay. And remember, it doesn't matter if this is less than or equal to when it's a continuous distribution. For discrete distributions, like the binomial distribution, that does matter. That makes a big difference, right? But for this one, continuous distributions less than or equal to end up having the same value. Any other questions? Not seeing anything coming in. Okay, great. So we're going to went to tutoring. Somebody's asking about NCR. So NCR, so you're asking about when the appropriate time to use NCR is. NCR is the binomial, is part of the binomial formula. So that's when we're using the binomial probabilities. For these problems, we're using the normal distribution, so we wouldn't use NCR. What we're talking about there, let me just put this into context so people know what we're talking about. NCR is a button you'll see on your calculator. NCR is the same as N-choose-R, which that's the notation I used when we were talking about binomial probabilities. And that is n factorial divided by r factorial times n minus r factorial. And that comes into play. This is part of the probability formula for binomial for the binomial distribution. But we're not using the binomial distribution in this section. We're using the normal distribution, right? Because we have that central limit theorem telling us that the normal distribution works. So this is not relevant to this section. That was chapter 4 stuff. Okay. I'm not seeing any other questions. So what I'm going to do is talk about newer material today, and we're going to talk about using the central limit theorem to create confidence intervals. And confidence intervals are hugely important, and I know you've seen them if you've read news. They come up now and then. They tend to well, you'll see. Let me get my I got a presentation ready for this, so let me cue that up. Okay, share that screen. Okay. Now that we totally understand the central limit theorem, right, we can use it to do some real statistical analyses here. So in this section 5.2, we're talking about confidence intervals for a population proportion. And we're going to talk about how you actually, what this is all about is it's about trying to capture the population proportion, right? And that's that parameter is another word for anything like a proportion or a mean or any statistic that's measured from the entire population. So the idea here is that, I think I gave the example before, we were opening up a pet store and we wanted to know what's the proportion of people in this community that own pets? Because I might want to compare different communities to know where the best place to open a pet store is. So what I'm interested in is what is the proportion of people that own pets in this community? I want to estimate that. So what I do is I go out and take a sample, and I get a sample proportion of people who own pets. Now I don't expect that to be exactly right because it came from a sample, and we know that the proportions measured from samples vary from sample to sample. So what I want to do though is I want to use that estimate, that sample proportion, to make an estimate about where the population proportion, what the population proportion might be. And that's what a confidence interval is. It's a range of values where I'm fairly certain that the true proportion is in that range, okay? And we're gonna start by constructing 95% confidence intervals. We're gonna construct an interval for which we're 95% confident that such an interval is gonna contain the real proportion. And then we'll talk about other confidence levels instead of 95%. And then, well, let's go ahead and start this. So capturing the population parameter. So using just a point estimate, and what is a point estimate? That's just a sample proportion. That's when we just go out, we sample a bunch of people, and we compute a proportion from that sample. That's a point estimate. It's a single number that we computed. That's like fishing in a murky lake with a spear. We can throw the spear where we saw a fish, but we'll probably miss. Our sample proportion probably isn't exactly right. You shouldn't expect it to be exactly right. On the other hand, if we toss a net into the area, we have a good chance of catching the fish. Right? So this is the idea of confidence intervals, that a net is better than a spear. So here's an example. 2 newspapers use data from a recent poll to report on the percentage of people who smoke. Which paper do you trust more? Okay. Paper A reports that 13.2% of people are smokers. Paper B states that with 95% confidence, the percentage of smokers is 13 plus or minus 4%. Well, which one would you trust more? Well, naively, a lot of people would tend to trust paper A because the value here is more looks more precise, right? It's got a decimal. It looks like, wow, that's a very, you know, accurate like measurement there. However, when you think about it, this is from a sample, right? They just sample, it's from a poll. So we know that samples generally don't exactly hit the true, they're not going to give you the true population proportion. It's just going to be an estimate. So even though they've got it down to, you know, the 10th decimal place, they went 0.2, I'm almost certain that they're not right. Because it's very unlikely that with that one sample that they hit the true population proportion spot on. It's like trying to fish with a spear. They almost certainly missed it. So I'm nearly 100% certain that they're wrong. All right. Whereas paper B has something a little bit more, they have a more broad estimate here. They say the percentage of smokers is 13 plus or minus 4%. So that's between 9 and 17%. Now that's not very precise, but it has a much higher chance of being correct. So I trust that statement a lot more than I trust the previous statement. And what this is, this 13 plus or minus 4%, that's an interval of values. It ranges from 13 minus 4, that's 9, to 13 plus 4, that's 17. So it's a range of values from 9 to 17. That's an interval. And the confidence, how confident they are that the true proportion is in that, the true percentage in this case, is in that interval is 95%. So they're admitting that there's a 5% chance that they're wrong, that the actual number of smokers is outside of this interval, but they're 95% sure that it is. So I trust this result more. So this is the kind of thing that we want to construct. And I hope you've seen things like this in the news and the media. They'll give you a number plus or minus some other number. Well, what they're doing is they're giving you a confidence interval. And if they're really good, they'll even give you the confidence level, which is this percentage, how confident they are. They tend to not write that down. They tend to just do 95% and just assume that everybody knows that, even though most people aren't aware. All right, so let's go on here. So, oh, this is basically what I said. So even though paper A seems more precise, but with this level of precision, they are almost certainly wrong. Paper B admits the possibility of error. That's the plus or minus 4%, and backs up their statement with a level of confidence. So assuming they use correct methods, paper B's result is better. Okay. So how do we construct these intervals? How do we come up with that plus or minus 4%? Well, that's the central limit theorem. That's what it's going to do for us. So it says that the point estimates we obtain from samples closely follow a normal distribution. Okay, this was the central limit theorem. When the central limit theorem conditions are satisfied, it says that the point estimate closely follows a normal distribution. So it would look like this. These are all the different sample proportions that we measured. This is how they'd be distributed. We have the mean here and the standard deviation, also called the standard error. So and it's centered where the true proportion is. So the question is, how big of a net do we need to ensure that point estimates will capture the population proportion 95% of the time? Okay. Well, in a normal distribution, 95% of the data is within 1.96 standard deviations of the mean. So our net should extend 1.96 times the standard deviation, that much, 1.96 standard deviations to the right and to the left of our point estimate. So we're going to take our point estimate and we're going to move away from it that far to the left and to the right. And then we have an interval. And such an interval, 95% of such intervals should contain the mean here, which is the true proportion. Okay. Where did this 1.96 come from? Well, if 95% of the data, we're saying that 95% of the data is within that many units of the mean, all right? Well, that means that 5% is outside of that range, which means that 2.5, half of that is to the left, and 2.5 is to the right. So let me just show you in StatCrunch how you to come up with that number. Where did my button go? Here it is, stop share. All right, so let's share my browser. Okay. Actually, we might not need that 2.5% because we can do this between business. All we're doing is in StatCrunch, you can just set up a standard normal distribution with mean 0 and standard deviation 1, and just ask, if I want to contain 95% of the data, what values have to go here and here? Well, look, I have to go from negative 1.96 to positive 1.96. That's where the 1.96 comes from. These numbers down here are standard deviations. The standard deviation here is 1, right? So it's saying that 2 standard deviations to the left and 2 standard deviations to the right contain 95% of the total amount of data. Hold on one sec. I think I saw a chat message come in. I'll get to that in just a second. All right. So that's where that 1.96 comes from. 2 standard deviation, 1.96 standard deviations to the left and 1.96 standard deviations to the right. Okay. Now you might remember the empirical rule. The empirical rule said that about 95% of the data falls within 2 standard deviations to the left and 2 standard deviations to the right, within 2 standard deviations of the mean. Well, all they were doing is they were just rounding this number up to 2. So 1.96 is a more precise measurement than 2. So we're being more precise than the empirical rule here. Okay, let me check out these chat messages here. Can you repeat that, please? Repeat which part? I'll go back to the. So what we were talking about is where that 1.96 came from. Okay. So what I did is I went to StatCrunch and I set up a normal distribution. Let's just nuke this. Put some other values in here. Okay. I went to StatCrunch and I said, I want to contain 95% of the data. All right. So let me go to the most basic normal distribution I can think of, the one with mean 0 and standard deviation 1. Right. How many standard deviations do I have to move away from the mean to contain 95% of the data? So I just put 0.95 here. And when I hit compute, StatCrunch sets it up. In this red area, it's set up so that it's 0.95. It contains 95% of the data. And if I look down here, the value, this is the value on the left, and this is the value on the right. So this is saying that 95% of the data lies within 1.96 standard deviations of the mean. Okay, so we got that from StatCrunch. And that is where this came from. In a normal distribution, 95% of the data is within 1.96 standard deviations of the mean. Okay. Okay, so a 95% confidence interval is our point estimate. We're going to go out and take a sample, measure a proportion from the sample, and then we're going to add or subtract 1.96 standard deviations. And you can compute the standard deviation because you've got that formula. So that's how you construct your confidence interval. I'm going to talk a little bit more about this just so we get a conceptual idea of what's going on here. So suppose we repeated our study. Why do you call it 95%? This is another way to visualize this. Suppose we repeated our study many times and constructed a confidence interval each time. So, or maybe I had, every single one of you go out and measure a proportion of people who own pets. Okay, so all of you come back to me with a different point estimate, a different p hat. All right. here's what we'd expect to see. These little blue dots here below the distribution are your different p hats that you came back to me with, right? You all got a variety of different values. The one is red just because it's way off, right? So somebody's going to be unlucky and just get a value that's way off. The lines that extend through the point estimates, these are the confidence intervals. This is the point estimate plus or minus 1.96 standard deviations. So it makes an interval. And you'll notice that even though the point estimates don't always hit, they almost never hit the actual population proportion, the intervals do. And in fact, the intervals are hitting the true population proportion 95% of the time. There is one out here that doesn't hit the population proportion. That interval does not contain the right value. So that's going to happen about 5% of the time, and that's just tough luck. You know, we have to accept that there's going to be some error here. 5%. 5% of the time we're going to miss. And just going back to the fishing example, these little point estimates here, these little points, these are our sample proportions that you brought back to me. These are like our spear strikes, right? We're trying to catch that fish. We keep missing, missing, missing. Every once in a while, somebody got it, right? But most of the time we missed. Once we were way off. The intervals here are our nets, right? So we expand around our spear strike and build a net. And now, instead of missing most of the time, we caught the fish most of the time. In fact, we caught the fish 95% of the time. We only missed 5% of the time, just in this red bar right here. Okay, so we've learned how to create a 95% confidence interval for a proportion. But it works for any parameter, even means and sums and things like this. It's not just proportions. And so some of the videos you watch in that section in My Open Math, you'll see they talk about the sample mean. It works the same way, exactly the same formula. I only have you do proportions though. So here it is, all summarized. When the distribution of a point estimate qualifies for the central limit theorem, so the conditions of the central limit theorem are satisfied, we can construct a 95% confidence interval using this formula. Okay, so we're going to use this formula for in this example, chronic illness. Okay, let me go to. I have this on another document so I can write on it. Should be seeing my Word document here. Let me make this, oh, not that. Let me make this a little bit easier to see by widening the margins, and let's increase the font size a little bit just to make sure that everything is clear. Okay, here we go. So, in 2013, the Pew Research Foundation, a real foundation, reported that 45% of US adults report that they live with one or more chronic conditions. And the standard error for this estimate is about 1.2%. So they gave us the standard error. Ordinarily, you'd be computing this, but let's just take it that we have it given to us here. Create a 95% confidence interval for the proportion of US adults who live with one or more chronic conditions. Interpret the confidence interval in the context of the study. Okay, well, we know the confidence interval is E hat, right? Plus or minus 1.96 times the standard deviation of the sampling distribution, or the standard error. Okay, that's how we're going to construct our confidence interval, right? Let's see, what's p hat? That's our sample proportion. Well, that's the thing that Pew Research Foundation reported. They took a sample and found that 0.45 of the proportion is 0.45 here. So our p hat is 0.45. Let me This is an equation again. So we're going to do plus or minus 1.96 times the standard error, and they gave us the standard error. So it's going to be 1.96 times 1.2. Oh, that's a percentage. We got to convert it to a proportion. 0.012. All right, as a proportion. Be careful to do that. All right, that'll be it. But we can compute this 1.96 times 0.012. Let me do that quickly. I get 0.0235. All right. So 0.045 plus or minus 0.0235. So that's one way to write down the confidence interval. Okay. Another way to write it down is to actually do the subtraction and addition. So in other words, we could write, we can say the interval, excuse me, is 0.45 minus this. So 0.45 minus 0.0235, that's 0.4265. Oop, forgot the 5 there. To 0.45 plus this amount. So if I add that, $0.4735. That's another way to write it down. Same thing, right? So that's what plus or minus means. Once you subtract and then you add, and the interval ranges from this value to that value. How do we interpret the confidence interval in the context of the study? What we're saying is that with 95% confidence, we expect the true proportion of US adults who live with one or more chronic conditions is, I either say this or write it like I did down there. So with 95% confidence, we believe the proportion of, let me just copy this. US adults who live with one or more chronic conditions is between these values here. So that's how I would write my response. Okay. Okay, I got a question here. Where did you get the 0.0235? All right. So that was just the 0.0235 just came from 1.96 times 0.012. Right? It's just 1.96 times the standard error, and they gave us the standard error, right? That was just given in this problem. So I just multiply 1.96 times this number. Okay. Okay. Notice I'm giving a confidence level along with my interval. All right, and that's very important that you report both. In the media, a lot of times they omit this because it's almost always, it's just assumed to be 95%. But in this class, we should be clear about it, all right? Because we can actually do different confidence levels. So let's be clear about which one we're doing. Okay. Let's do, let me look at my, yeah, let's do another one here. Let's do this next one. Pew Research conducted a poll of 1,000 American adults and found that 88.7% of them supported expanding the role of solar power. compute and interpret a 95% confidence interval for the population proportion. Okay, well, we know our formula. It's going to be p hat plus or minus 1.96 times the standard error. I know it's 1.96 because it's a 95% confidence interval, and you're just going to have to remember that 1.96. Okay. Now, what do we know in this problem? Well, p hat, I think we have. In this sample here of 1,000 American adults, I can see that the percentage is 88.7. So I can convert that to a proportion, 0.887. That's my p hat. Okay. What else do we have in this problem? Do we have the standard error? Well, no, they didn't give that to us. Okay, so we're going to have to find that. Okay. Well, to find that, we're going to need to know n, the sample size. Do we know that? Well, yes, because it says right here, the poll was of 1,000 American adults, right? So I know that n is equal to 1,000, okay? And so from that, I can compute the standard error. The standard error, or sigma, the standard deviation of the sampling distribution, is the square root of, it's p times 1 minus p divided by n. Right? That was the formula. Now we're going to make some adjustments here. All right. P represents the true population proportion. We don't know that. That's actually what we're trying to estimate. So I mentioned before, either last class or the class before, that when we don't have that, what we use is the next best thing. If we don't have p, we use p hat. Oh, that didn't work. Let me try that again. If we don't have p, we use p hat. All right. That's our best guess. All right. P hat is the thing that we had from our sample. The difference is p hat comes from the sample. P comes from the whole population. That's the difference. Okay. So well, let's compute it. It's going to be the square root of, well, p hat is 0.0887. Nope, not 0.887, just 0.887. And then we're going to multiply that by 1 minus p hat. So take 1 minus that, you get 0.113. And n is 1,000. All right. It put this outside, out front, the fraction, but that's okay. That's going to give us the same answer. Okay. So this is going to be approximately equal to, I'm going to go do this on a calculator. All right. So I'm getting used to this calculator. Can't find the square root button. All right. Okay, I'll just raise it to the power 1/2 then. That's the same thing.
It's equal to 0.0100.
Yeah, well, yeah, let me just double check. My calculator is not giving me what I want. You might be right, but I'm going to check it myself. Yes, you are spot on. Thank you. 0.0100. Yeah. Very good. Thanks. All right, that's the standard error. All right, but then we have to multiply that by 1.96, right, to get this thing over here. All right. Now multiply by 1.96. 0.0196. Well, that makes sense. All right, so so the confidence interval, all right, is given by, there's two ways to write it, okay? The first way is to just write it down as, like we have right up here. So it's gonna be 0.887 plus or minus 0.0196, or we could write it like this. We could say, we can actually subtract 0.0196 from this number, right? So .8674. Like this, between this and then I can add 0.0196 to 8.887. And I get 0.9066. Same thing. There are two different ways of writing the same thing. Okay. On one hand, I just put plus or minus. On the other hand, I actually did the plus and minus. It actually performed the operation there. Compute and interpret a 95% confidence interval. So we are going to write down a sentence to interpret what we have here. All right, let me just save some space by deleting some empty lines here. Okay. Let's see, what did the problem say? It's the American adults who support expanding the role of solar power. Okay. With 95% confidence, we believe the true proportion of adults who support expanding the role of solar power is between, and then those numbers that I wrote over here. So, da, 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 da. Or if you wanted to write it in terms of percentages, you could make these percentages. So we could do this. Just to be a little different, just in case you can do percentage. Okay. So between 86.74% and 90.66%. Okay. Let's do this one about dental visits. Okay. In a survey of, oh, my computer froze a little bit, it'll come back. In a survey of 674 US males aged 18 to 64, 396 say they have gone to the dentist in the past year. Compute and interpret a 95% confidence interval for the population proportion. All right, well here, we need to find p hat. All right. Well, p hat is what? Well, let's see. In a survey of 674 males, 396 say they've gone to the dentist. So, okay, well that's 396 divided by 674. Right? So 396 divided by 674, that's 0.5875. I've rounded, so I put approximately equal to. So here I had to compute the population proportion from the numbers that were given. Right? What's n in this problem? Well, that was my denominator there. N was the sample size, 674. All right. I'm going to need my standard error, right? The standard error is given by the square root. Let me just copy it from above to save some time here. Here it is. And that's going to be approximately equal to the square root of, well, our proportion is 0.5875 times 1 minus that, which is 0.4125, divided by the sample size, which is 674. Okay. So here we go. 5875 times 0.4125 divided by 674. And then I'll take the square root, and I'm getting 0.01. I get 0.01896, but when you round that up, you get 0.0190. 0.0190. Okay, so my confidence interval is, oh wait, I still have to compute 1.96 times that, right? Yeah. So I'm going to multiply that by 0.19. Okay, somebody's scribbling on my screen. You gotta ease off on that. Let me see if I can figure out how. Oh, thank you. Okay. So 1.96 times that is what I'm going to compute. All right. So I get 0.0372. All right. Let me put that in the center with the rest so that it looks normal. All right. So that's the 1.96 times the standard error. So this is the thing that I'm adding or subtracting from the population proportion. All right. So my confidence interval is, one way to write it is to write the population or the sample proportion plus or minus that number. Or another way to write it is to say that it's between the two values that I get by subtracting and adding that number. All right. So I'm going to take 0.5875 and subtract 0.372. That's 0.5503. Oh, 5503. And then I'm going to do the same thing, but add that number. .6247. Right. Two ways of writing the confidence interval. And interpret it in the context of the problem. Have gone to the dentist in the past year. That's what we're talking about. And these are US males. So with 95% confidence, we believe that between, let's do these in percentages, 55.03% and 62.47% of US males have gone to the dentist in the past year. Okay. So there we go. Any questions on that? Okay, one thing I want to point out here is that when we take this 1.96 and multiply it by the standard error, that's what we're adding and subtracting each time. That thing right there is called the margin of error. Right, so just to point out, I just want to point that out. The margin of error is the 1.96 times the standard error. That's the margin of error. The margin of error is the thing that you're adding or subtracting from your point estimate. So another way to write down the confidence interval formula is just to say that it's equal to p hat plus or minus the margin of error. Right? Plus or minus, that's how much we think we might be off by. So it makes sense that that's the error, right? So you might see that word, margin of error, used in some homework problems and things like that. All it is just the 1.96 times the standard error, okay? It's just this number that you're seeing right here. The margin of error in this problem is 0.0372. The margin of error in this problem was the 0.0196. The margin of error in this problem was the 0.0235. Okay. Notice sometimes I answered these questions in terms of proportions, sometimes in terms of percentages. That just depends on what's being asked. Okay, so you should be able to do it both ways. All right. So, by the way, I'll save this document when I'm done and I'll post it in the course materials if you want to reference it. Okay, so one last thing that we need to talk about is how to do other kinds of confidence intervals. So what we just talked about was the 95% confidence interval. What about a 99% confidence interval? Or what about a 90% confidence interval? Or what about an 85% confidence interval? How do we do different confidence levels? All right, so let's just take a look at how we do that. It's actually very simple. Once you know how to do 95%, the other one's super, super easy. Give me a second here. I got to make sure that, okay, that should work. I share this correctly. Here it is. All right. So we did these examples. Changing the confidence level. Okay, suppose we want to consider confidence intervals where the confidence level is higher than 95%, such as a confidence level of 99%. So think back to the analogy about trying to catch a fish. If we want to be more sure, 99% sure instead of 95, that we catch the fish, should we use a wider net or a narrower net? Well, of course, a wider net. A wider net will be more likely to catch the fish, right? So we're going to have to widen our interval, make it bigger, in order to get a 99% confidence interval. So to create a 99% confidence interval, we must widen our interval. On the other hand, if we wanted an interval with lower confidence, such as 90%, we can use a narrower interval, a smaller net. So with a smaller net, we're more precise. We're saying we're the values within a tighter range, but we're less confident that it's actually in there. So there's a trade-off here. The more confident we want to be, the more error we need to introduce. If we're willing to be less confident, we can have very little error. So if we would want to be 90% confident, we can use an interval of very little error. So there's a trade-off here. So let's see how to construct these. So recall the construction for a 95% confidence interval. When the it's the point estimate from a plus or minus 1.96 times the standard error. Right? That was the formula. What made it where did the 95% come in? Well, remember, that's when we went to Stack Crunch. I typed in 0.95 and then it spat out 1.96. Okay, so the number 1.96 is the part that came from the 95%. So what if we change this to 99%? If x is a normally distributed random variable, how many standard deviations away from the mean will capture 99% of the data. So we got to get a new number, not 1.96, but something else. What would that number be? Well, let's just go back to StatCrunch, and we will plug 0.99 in instead of 0.95. So here we are in StatCrunch, and it's all set up. I just have to change, since my computer unfreezes here, I just have to, there it is. I just have to change 0.95 to 0.99. And there we have it. X has to be within 2.5758 standard deviations. Let's just round that to 2.58, all right? So instead of 1.96, we're gonna use 2.58. Or if you want to be more precise, go to more decimal places, 2.576, something like that. I'm going to use 2.58. So back to the slideshow here. If a point estimate closely follows a normal model with standard error, with this standard error, then the confidence interval is always going to look like this. It's going to be the point estimate plus or minus the z star is the number that we're going to use multiplied by the standard error. So if it's 99%, z star is going to be 2.58. If it's 95%, z star is going to be 1.96. If it's 90%, I'll let you figure out what z star will have to be. You can do that on your own just by doing exactly what I did in StatCrunch. Maybe we'll do an example like that down here, I'm not sure. And this margin of error, this is exactly what I was talking about on the document previously. The z star times the standard of error. The thing that we're adding or subtracting from the point estimate is called the margin of error. Okay, so let's go ahead and do, for this example down here, the solar power example, let's compute a 99% and a 90% confidence interval. Okay, looks like the same problem we had before. It's just that we're computing a different confidence interval, different type. Okay, so let me go back to our examples. Okay. I think we can answer this question. We said it was how many standard deviations for a 99% confidence interval. It's going to be 2.58. We'll use that in this problem. So let me. So Pew Research conducted a poll, same problem, of 1,000 American adults, found that 88.7% of them supported expanding the role of solar power. Compute and interpret a 99% and a 90% confidence interval. Okay, well, like we said before, n is equal to 1,000. P hat is equal to 0.887. The standard error, we computed that before, right? Let's just go back and see what we had up here. We computed that up here and we got 0.01. Oh, that's nice. Okay. 0.0100. Same computation as before, nothing's changed yet. The thing that's going to change here is that our confidence interval, so our 99% confidence interval, is going to be P hat plus or minus 2.58. 2.58 times the standard error. Okay, that's the difference. Instead of 1.96 times the standard error, it's 2.58 times the standard error. So P hat is 0.887. What's 2.58? Sorry, yeah, what's 2.58 times the standard error? Well, it's 0.20258. Okay. So that's our 99% confidence interval. Okay. I'm not going to do the plus and minus part because I think we've got that figured out. What about a 90% confidence interval? Well, that's going to be p hat plus or minus. Okay, it's going to be something times the standard error, but it's not going to be 2.58. That's the one that corresponded to 99. What corresponds to 90? Okay, well, let's go and compute that one. Okay. Okay, so we're going to go back to StatCrunch, right? And we're going to do 90. So just put 90 in there. Looks like it's 1.64 this time. 1.64 standard deviations to the left or right of the mean gives you 90%. So that's the number we use. Sometimes I use 1.645. Let's do that because that's what I'm used to seeing, 1.645. So let's go ahead and use that one. .645. Oh, not typing. 1.645 times the standard error, which is the 0.01, right? So it's going to be point estimate plus or minus. If I multiply that by the standard error, you guessed it, it's 0.01645. Round that up to 0.165. Okay, so that's our 90% confidence interval. Okay. Notice that the margin of error is smaller for a 90% confidence interval. Right? If we want to be less confident, we can get away with less error. You can use a smaller net. You're less sure that you're going to catch the fish. That's the idea. For the larger 99% confidence interval, if we want to be more confident we catch the fish, we need to have a larger margin of error. Okay? So keep that in mind, that there's that trade-off there. Higher confidence, more error. Okay. All right, let's look at another problem here. Let's look at the influence of sample size. So the size of our sample plays a big role in what we're doing here. Okay. Let me also just check the chat window and make sure there's no pertinent questions coming up. Oh, where did the chats go? Not seeing the chats. Clicking chat, but it's not showing up. I know if I stop sharing, I can see them. Nope, nothing new coming in. Okay, going back. Okay, so suppose data collected on 100 subjects gave rise to a confidence interval of 38 plus or minus 6%. Okay, so 38% plus or minus 6%. How must the sample size be changed in order to produce a confidence interval with a margin of error half as large? So see, I've got this margin of error of 6% here. Maybe that's too big for me. Maybe my boss wants me to be more accurate. Okay, he wants a 3% margin of error. Okay, so I got to go do this study again. How do I have to change my sample size? How many more subjects do I have to ask in order to get a smaller error? Okay. Well, where does the margin of error come from? Okay, well, the margin of error comes from the standard error. we multiply some number depending on the confidence level. So it's 1.96 or 2.58 or 1.645, depending on the confidence level. We're going to multiply this thing, standard error, by that number. So let's see how standard error is influenced by the sample size. So let me go get the formula for standard error here. Right there. Paste it in. Okay. So looking at this formula, I can see that the sample size is in the denominator. Right? So if I increase the sample size, I'll make the standard error less. Right? Increasing the denominator makes the fraction smaller. So you might say, well, if I double the sample size, I'll have a fraction that's half as big. And you're right, except that the standard error has a square root, right? So if I want something half as big, to get a 2, I need to take the square root of 4. So really, to get a margin of error half as big, I have to multiply my sample size by 4. Right? Because if I put a 4n down here, right, that will be, let me just copy this. That's the same as, see if this will let me do this, 1/4 times this, right? But that's the same as, oops, that's the same as the square root of 1/4 times the square root of this. But the square root of 1/4 is 1/2. So I'm actually getting a half of the original standard error, right? So if I amplify the sample size by 4, I cut my standard error in half, which cuts my margin of error in half. So if data on 100 subjects gave a confidence interval this big, if I want to cut the margin of error in half, I need a sample size 4 times as big. So we need to sample 400 subjects. 4 times as large makes the margin of error half as big. Right? Okay. Besides adjusting the sample size, what else could be done to decrease the margin of error? What else could we do? Well, remember, the margin of error is, it's that Z star. Oh, how do I do a star without making it a multi? Yeah, Z star times, and I don't want to use an asterisk because I don't want to confuse it with the star, times the standard error, right? So I can also cut the margin of error in half by adjusting Z star. Where does Z star come from? That comes from my confidence level, right? Different confidence level, we use a different number here. So if you want to decrease the margin of error, you want to use a different confidence level. So I want to make a smaller net. We mentioned before that I need my confidence level to be less. I need to be less confident. So to decrease the margin of error, we decrease the confidence level, all right? The amount you have to decrease it, you'd have to play around with that in StatCrunch and look at the normal distribution. I'm not going to ask you exactly what. It depends. It depends on what confidence level we had to begin with, and then you'd have to find the Z star that would actually give a half of the other Z star, right? The confidence level that would give you a new Z star that's exactly half of the first one. But it could be done. But the idea is you'll have to decrease the confidence level. And this is the last question, all right? So this is our last problem. Let's go to a new page. All right, waiting at an ER. Okay, A hospital administrator hoping to improve wait times decides to estimate the average emergency room waiting time at her hospital. Makes sense. She collects a simple random sample of 64 patients. She can't sample everybody, so she looks at 64, and determines the time in minutes between when they checked in until when they were first seen by a doctor. So how long are they waiting? A 95% confidence interval based on this sample is 128 minutes to 147. So with 95%, well, I won't say this because I think I'm answering one of the questions below. All right, so that's our 95% confidence interval, this range of values, which is based on the normal model for the mean. Right? That's what we've been using from the central limit theorem. Determine whether the following statements are true or false. Okay, so let's look at these, just making some space here. We are 95% confident that the average waiting time of these 64 emergency room patients is between 128 and 147. True or false? Let's see. 95% confidence that the average waiting time of these 64 emergency room patients. Well, the 64 is the size of our sample. We actually know, we took the sample. We know exactly what the average waiting time for a sample is. The confidence interval is not about that. We know exactly what the average waiting time for a sample is. That's the average that we would have computed, right? That's the sample estimate. That's the point estimate. So no, that's not what the confidence interval is about. So no, that's false. We know the point estimate, the one from the 64 patients, exactly. We don't need a confidence interval for that. That's silly. That's not what the confidence interval is about. The confidence interval is about the population. Okay. Point estimate, I should be more precise, from the sample, right? That's the 64 patients. We know that exactly. We don't need a confidence interval for that. How about part B? We are 95% confident that the average waiting time of all patients at this hospital's emergency room is between this and this. Yeah, that's what the confidence interval is about. It's about the entire population. So this is true. Oh, true. Yep, that is what the confidence interval is about. What about part C here? About 95% of random samples will have a sample mean between this number and this number. About 95% of random samples will have a sample mean. All right, this one's tricky, and what a lot of people would say is true here, but the answer is false. All right, what we're doing, we built a confidence interval around our point estimate. And what we're expecting is 95% of the point estimates to fall within a certain range of the actual mean. We don't expect 95% of the point estimates to fall within our point estimate. We expect them to fall within a certain range of the actual mean, the actual parameter. So this is kind of thinking about things the wrong way. It's centering things around the point estimate instead of the actual parameter. So this is false. The 95% of sample estimates should fall within one margin of error, whatever that is, of the true parameter, whatever we're measuring here. It looks like it's the population mean in this case, not the point estimate, which is what this interval is centered around. All right. It's a subtle idea, but that's the way it works. I'll let you ponder that a little more if you didn't understand it right away. A 99% confidence interval would be narrower than the 95% confidence interval, since we need to be more sure. well, wait a minute. If we're more sure we're going to catch the fish, we need a bigger net. So the 99% confidence interval should be bigger. So that's wrong, false. 99, more confidence requires a bigger interval. Okay. And finally, the margin of error is 9.5 and the sample mean is 137.5. Well, let's see, does that work? I take 137.5 and then I'll make this into an expression here. And then I add or subtract 9.5. What do I get? Well, if I subtract 9.5, I get 128, right? And actually, I don't want this to be written like, okay, I get 120. I don't want this to be an equation. Okay, 128. If I add 9.5, I get 147, right? Is that the interval that we're dealing with here? Yeah, 128 to 147. So this is the same as this, right? So if I add or subtract a margin of error from the sample mean, I get exactly the confidence interval we're talking about. So yes, this corresponds exactly to what we're doing. So yeah, true. True. Yeah, adding or subtracting 9.5, the margin of error, from 137.5 gives the confidence interval that we're dealing with. Okay. Because that's how the confidence interval is constructed. They're just kind of deconstructing it here. They're giving you the error and the mean, and then yeah. All right. Okay, that's all I have. We went a little bit long today. Sorry about that, but we covered all this. We'll review a little bit of this next time. So, are there any questions? Am I going to post a new lab? I might post a new lab next time. I'll let you know next time. I'll send an email in advance if I do. All right. You won't need to be on StatCrunch during the discussion though. So, but do be ready with lab 3 so that we can go over it next time. Any other questions? Okay, just want to remind everybody the exam is in 2 weeks. It's the Tuesday after next Tuesday. I'll open up some old homework so you can practice those before the exam. I'll post copies of them. There'll be a problem or two that require you to show work. I'll give you an idea what kind of problem that will be so that you can kind of prepare for that. I'll give you more information about that as probably next week, all right? Okay, so I need to let my computer process this video before my next class, so I gotta head out. So I'll see you guys on Thursday.
Take care, Professor.
Thank you.